Okay, your next mini exam is due on Wednesday, right? Wednesday? We have our midterm. All right, we have our midterm scheduled. Whoa.
My bad.
You all right, regular?
Yeah, I'm fine.
I said midterm and you freaked out. We have our midterm a week from today, right? A week from today. Would any of you want to have it on Wednesday instead? Well, some people are like loaded up that week with exams. Let's do a quick vote. How many of you feel like you'd prefer to have it on Wednesday, March 9th instead of Monday? Okay, well that's a majority. I'm still going to keep my promise that 11.7 will be where we stop, but that means that next Monday I will start doing 11.8. If I get, as soon as we're done with 11.7, I'm going to keep going. So just make sure that you remember that. You know, you don't want to get caught off guard after the midterm and, you know, I'm already past 11.8 and then it shows up at the final and you're like, what is this? Right? Okay. 11.7. Question, yes?
So then if you move on to 11.8, is it going to be on the midterm?
That won't be on the midterm. That's what I said last time, I think. I said our midterm will cover up through 11.7. Now, if we go through 11.8 and, you know, by the end of the week everyone's like, yeah, sure, put 11.8 on there. I think we're good with it. If that's what y'all decide, then I'll do that. But I don't want to go against what I said at this point. So it'll have to be another unanimous vote like that or strong majority. All right, so maximum and minimum values. You already had a take-home exam, a mini exam, where this is our new student. I'm not going to count off for you not being here. All right, so we already looked in Cal 1, right? On those mini exams, I said, I gave you a hint, a strong hint that you're going to have to go back and review how to figure out to do max and mins, right? And there were two different types of problems that you had in Cal 1 where you found maximums and minimums. One of them was on, anyone remember? Like how do you find the max and min of a function on a closed interval versus on an open interval? There's two different techniques. So let me remind you, I don't want to go back through and review all of this. I'll just do a quick reminder. Let's just say that we have from Cal 1 a function of one variable like x cubed minus, let's go with 3x squared, something pretty simple like that. We could do two things. We could either try and find local maximums and minimums of this function on its entire domain, or we could restrict the domain and look just on a closed interval. So I want to approach it both ways first. So right now, first, find local max / min for this function. So how do we do it? Take the derivative, set it equal to 0. Also, find out where the derivative does not exist. But in this case, the derivative will exist because, why is this derivative going to exist? It's a polynomial, good. All polynomial functions, when we take their derivatives, they're still polynomials, and those are nice, well-behaved functions. So we're going to do the derivative. Now you said set it equal to 0, right? So we set this equal to 0. And just factor now, right? I'm going to pull a 3x out. Be left with x minus 2. And then we just set those both to 0. So where are we going to have these critical numbers is what we called them, right? Remember that, critical numbers? Our critical numbers are 0 and 2, right? All right, now what? Do you remember? There's a couple of different options depending on your teacher and how you were, what was emphasized. So anyone have any recollection of what we do with these numbers now? You could do like a sign chart where you try and figure out where the function is going up and down. Yeah. Remember doing that?
We just did like a number line.
Number line.
Yeah. And then
Yeah.
Because the sign chart was just too much to do.
Okay, so I agree. That sign chart can be a pain in the butt. How about the second derivative test? Any of you remember the second derivative test?
Yeah.
Second derivative test was very convenient when the first derivative was equal to 0. The second derivative test told you exactly if it was a local max or a min. So what we had to do is we had to look at these values, 0 and 2. Let's look at the second derivative. Let's go ahead and put that up here. What's the second derivative of this function? 6x minus 6. Okay. And
Set that equal to 0.
set that to 0. Okay, if you set that to 0, what you're going to get are your inflection points, or possibly. That's where you're going to have your concavity changes. What we're interested in here is whether or not at these points we have something happening. So let me try and remind you with the picture. What we know right now is that if I were to graph this polynomial, right? It's third degree polynomial, so it has to go down on the left and up on the right. We think potentially that this is two x values where we might have a local max and min. What we do know is that at these points, we have a first derivative equal to 0, don't we? Which means that at these points, I have tangent lines. I missed a little bit there. We have tangent lines that are horizontal, right? But remember, we don't know what this looks like, right? We're just, thank you. What is this? Oh, it's not due today. It's due on Wednesday. Hey, you don't have to worry about it now. It's done. You got 2 days to not think about it. All right. I know a couple of y'all did the take home and had it ready for today. It's due Wednesday. All right, so we don't know this picture's here, right? So the second derivative tells us about concave up and concave down, right? So if I just take 0 and plug it into the second derivative, if the answer is positive, I'm concave up, and that would correspond to a local minimum. If I do the point in here and I get a negative, then it's concave down, then I have a local maximum. Remember this? Okay, so let's just check it real quick. Plug 0 in here. Plug 0, what's f double prime of 0? You get -6, which means at 0 you're concave down, which means that corresponds to a local maximum. Then if you plug in 2, you get +6, right? Positive number, so you're concave up, so it's going to correspond to a local minimum. This is just a reminder, okay? This isn't like, hey, let's go back and rehash up Cal 1. Because today what we're doing is we're going to have something called the second derivative test. But we're now going to be on a surface, and it's similar to this, all right? We're going to be checking things and comparing and seeing, and it'll tell us if we have local maximums or minimums. All right, so that's how we did this. This enough for us to move on? That's how we did it if we did not restrict the domain. Now, if someone comes in here and gives you this function and restricts the domain, now that's a different story. Okay, if they restrict your domain, like let's say between 1 and 7, then what could be happening here is that your function, let me draw it like this, might look like this. Again, I'm kind of making this up. We could graph it, I'm not going to. Our lowest point on this graph actually corresponds to the local min we would have got from the second derivative test, right? But the maximum does not occur on one of these humps. It actually occurs at an endpoint on the interval. So the way we did this was different than the way we did the last one. All we do here, set the derivative to 0 again, which we already know the answers, right? 0 and 2. Anyone remember what we do with those now? Plug the endpoints and these into the original function and compare. The biggest answer is your max, the smallest is your min. The only thing you have to be concerned about is whether or not one of these doesn't lie in here, right? And 0 doesn't lie in here, so we wouldn't worry about that. So we would just evaluate f of 1, f of 2, f of 7, and then it spits out answers, right? Understand? Remember? Recall? All right. With that in mind, let's move into today's stuff. All right, so what is today about? It's about the same thing, max and mins, But now we're looking at functions of several variables, in fact, 2 variables instead of just 1. All right, so this is a surface that I've gone ahead and graphed for you just because it has some important characteristics. It has these little hills on it. There's like these little ripples on our sheet that's floating through the air, right? Some of them are high, this is like the highest point on the graph locally, right? Like this person standing up here is king of that mountain, right? That's it, just that mountain. This one right here, king of the mountain there, right? So you got all these different ripples. We got local maximums all over the place. And then on the bottom, you have the same things, some effect of a local minimum. And what we need to do is see if there's a way we can find those, where those points are occurring. Just zoomed in on the same thing. And then this is straight out of your book. That's actually the same graph that I just showed you, but this is the book's version of it. And they just showing you some different language here. Local maximum versus an absolute maximum. Absolute maximum would be the highest on the entire function, on its entire domain. And we can go through and we can discuss the definitions, but I think more importantly for us is just geometrically understanding what these points are. We have some theorems. If your function has a local max or minimum, let me make this a little bigger, you can see this. This is right out of the book, so you can refer to it if you need to. Whoa, where'd it go? That's pretty funny. I'm saying zoom in and it actually got smaller. Okay. If your function f has a local maximum or minimum, if it has one, at a point a, b, and the first order partial derivatives exist, then they have to be 0. That's an important theorem. It's telling us that if you're going to ever have some top of a hill or some bottom of a valley on a surface, the first partials have to equal 0 there, which is very similar to what we just talked about back in Cal 1, right? We wanted to set our derivatives equal to 0 to figure out where we had flat horizontal tangent lines. Same concept here. But then we have this thing called the second derivative test, which is rather complicated to read here. Let's see if I have a better version of it. I thought I had a better version. It's really not coming out very clear up here, is it? I'll write it down on the board, okay, on the side here for us. Let me just get to an example so you can see this. So our goal here is going to be to find the extreme values of this function. All right, so the layout is this. We know that if this has a local maximum or a local minimum, if it does, it has to occur where the first partials are 0. That's what the theorem said. And then the second derivative test, which you can barely read, I'm going to write it down on the side for us. All right? So let's start, though, with just taking the first partials. So what is the first partial of this function? What's the partial with respect to x? Negative 2x. And let's take the partial with respect to y. What do we got? 2y? And that's it. So what we're trying to figure out now is where these partials are 0. So let's just set them each both equal to 0. So set partial of f with respect to x equal to 0 means negative 2x equals 0, which means x is 0. So in order for this to be equal to 0, right, the x-coordinate must be 0. Now we do the same thing for the partial with respect to y, and we get y 0, right? This is the first example. It's going to be easy derivatives and pretty simple outcomes here. So this tells me that if I'm going to have a local max or a local min, then it's going to be potentially at this point 0, 0. 0 for x and 0 for y. The way to actually determine whether or not it is a local maximum or a local minimum is to apply the second derivative test. So here's what the second derivative test says, and I will write it down on the board over here. Do you remember what we just did a second ago with the second derivative test? Is it was a test for concavity, and we did the second derivative, we figured out where it was positive and negative, right? This is similar, but it's going to look a lot different. We're going to compute this thing called capital D, which is not the domain, it's just capital D for second derivative test. It's going to be equal to the second partial of f with respect to x, so we're going to take the partial twice, times the second partial with respect to f again, but this time y twice. We're going to figure out what that is. We're going to subtract from it the partial of f with respect to x, followed by differentiating with respect to y, so that's another second partial, and then squaring that. That's the thing that we're going to look at, whether or not it's positive or negative. All right? Now, we're not here today to explain why it is that this is going to work, all right? That's a more profound question, but we're just going to trust it and go with it. Is that all right with you? Okay. I don't think the book goes into the explanation. I don't think it does. All right, we good? Yes? Now, we have some conditions, some outcomes. If capital D turns out to be positive, and the second partial with respect to x, so respect to x twice, this piece right here, if that's also positive, then you have a local minimum. All right? If capital D is greater than 0, so again, that turns out to be positive, and partial of f with respect to x, so that second partial again is negative, you have a local max. And the last thing that could happen is if D turns out to be negative, then you don't even need to care about this second partial at all. You have no max, you have no min locally, okay? No local max, no local min, and you have what's referred to as a saddle point. All right? Now, on this picture that you can see here, that kind of looks like a saddle, doesn't it? Maybe a little bit. I don't know how many of you have ever seen a saddle, but I think I've ridden a horse once, and I know that that looks like a saddle. So everyone should think that looks like a saddle. That's what I'm trying to say. All right, so I'm wondering if we'll get a saddle point. We'll see. Right now, here's what we know. Something interesting is potentially happening at 0, 0, right? That's what I know. So now what I'm going to do is I'm going to compute what D is. So in order to compute D, we need all these second partials, don't we? Let's go ahead and go get second partials. Let's just get all the partials taken care of now. Just remember 0, 0 right now. 0, 0 is this critical point for us. I'm going to say CP for critical point. So let's get the second partial here with respect to x, which would be -2, right? And then the second partial here with respect to y, 2. And then we also need partial with respect to x followed by y, which would be 0. Because I'm doing the partial of that with respect to y, so 0. So notice that now I can go over and compute what D is, right? What's D? Well, D is equal to the partial, the second partial, which for us was -2, right? And then followed by what? 2, and then minus 0 squared, and what is that? -4? -4. And so we should have a saddle point, right? The question is, where do we have a saddle point? At the origin, right? See, this was the point that was actually interesting to us, right? It turned out that when we calculated D, we actually didn't even need to refer back to this, did we? This capital D told us, look, if you have any points of interest that you're looking at, they're all saddle points because D is always negative. In the next example that we're going to do, you're going to see that these partials, these second partials, are not going to be constants. They're going to depend on x and y, and so the point that we're looking at will matter. This is the first example. It's the most simple example. So we good? Saddle point? So I'm going to summarize now. We have a saddle point. And it occurs at 0, 0, right? And what I'm going to ask for you to do on the test and on anything you do take-home-wise is give me the ordered triple. Okay? We know it occurs when the x is 0 and the y is 0. But go ahead and give me the z value too, the function's value. What would it be here? 0 in this case. Just plug 0, 0 in there, right? You got 0. So at that actual point on the graph, right there, that's a saddle point. All right? No questions? Yes?
You said on the next example,
Mhm.
the d being negative will tell us that it's a saddle point anywhere that we can see?
No, on the next one, when we do these second partials, they aren't going to be constants. They're going to be more complicated. And so that critical point that we found will actually matter. See, here we said d is always negative, right? And so that means any critical points I had would guarantee to be saddle points. All right, so let's look at another one. Yes? Uh-huh.
Why are we only considering the second partial with respect to x? Why not y?
Which one? What do you mean?
Like when we're looking at that.
Like,
Well, not that, the first part of it when we have.
well, that's what I'm saying. If you want to get into the details of this theorem, then that's going to require more of like a sit-down conversation in my office. I mean, you can start to try and understand it by thinking like this is almost like a concavity, isn't it? Second derivative with respect to x is like a concavity. So like, see, I'm going to go way too far off a tangent here. But if you have a concavity that goes like this, that's with respect to x, and then another one that is perpendicular with respect to y, then look, if they're both positive, right, then you're looking at maybe being a local minimum. As opposed to one being positive and one being negative, you're looking more like a saddle. But that's not all you have to look at. You have to look at this one also, because that can have an effect. So it becomes a little more complicated. I'm just trying to explain why these two pieces might be important to you. Understand?
Yeah.
Okay. All right, this one, where's my little mouse? We won't look at the function yet, okay? We'll come back and look at it. Let's just take the actual function up there, and we'll look at its graph in a minute. Find the local maximum, minimum values and saddle points or saddle point or points. So we've got this function of two variables. You have kind of different approaches that you can take on this. You can just say, hey, look, I'm going to first figure out where the partials are equal to 0. Get all my critical numbers first, critical points. Then I'm going to go compute d. Or you can say to yourself, look, I'm going to need all these partials, right? Let me just go get them all now, and I'll sort them out later. It's really up to you. When I did the video of me doing the homework problems for this section, which are not posted, by the way, yet, I did it both ways. I just kind of mixed it up. So what I'll do first, I think I'm going to get all the partials out of the way. Is that all right with you? Because these look like they're going to be pretty easy partials. What is, do I need to make that a little bigger? There. It's the partial of f with respect to x. 4x cubed minus 4y. Do we have agreement? Okay. We're going to need the partial again of that with respect to x, aren't we? So what's the partial with respect to x again? 12x, right? Squared? I'm going to need the partial with respect to y, which is 4y cubed, good, minus 4x. I'm going to need the partial of that with respect to y again. 12y squared. And there's one more partial I'm going to need if I'm going to do all this, which is the partial with respect to x followed by the partial with respect to y. So just this one up here, take the partial of that with respect to y, which would be -4. So fxy -4. Is that all right if I say it like that? fxy? Everyone understands what I mean? All right, so that's all the information I'm going to need. And now let's get to the computations here. I'm going to first find the critical points. All right, so I'm going to do what to find the critical points? Set the partials equal to 0, right? Okay. Go ahead. A little more complicated than the last one. This is where things start to get a little bit messy. When you look at that first partial set to 0, you have one equation and two unknowns, right? So you're not going to be able to solve that, and get an exact value for x and y. There's an infinite number of solutions to that. But you also need the other condition to be met, right? And you need the partial of f with respect to y to be equal to 0. And that's the other equation, 4y cubed minus 4x equals 0. So now you really have two equations, right? And two unknowns. But these are nonlinear equations. So you cannot use matrices. Can't use linear algebra to solve these because they are nonlinear equations. So you need something else. So wait, did I write that? Yes, I did. Okay. Anyone have any ideas what you want to do here? Substitute? So how do you mean? Substitute.
Solve for x or y.
You want to solve for x over here and then plug that in over there? Sure, we can do that. So solve this for x. You get, let's say, 4y cubed equals 4x, and then that means y cubed is x, right? And then what I can do is I can go over there, and I can replace what with what? X with y cubed. So come over to this equation and rewrite this, replacing x with y cubed. So that's actually going to become y cubed, what? Cubed minus 4y equals 0. So I'm using this right here to go solve over there. And what's 4y cubed cubed? 4y to the 9th minus 4y equals 0. And now you get to solve that. How do you solve that? Factor? GCF? They have a greatest common factor? Do they? What's the greatest common factor here? 4y, right? Pull a 4y out. You're left with y to the 8th minus 1 equals 0. Set each of those equal to 0. I'm running out of room over here, so I'm just going to do it over here. 4y, set that to 0. And y cubed, y to the 8th, not cubed. I wish it was cubed. Y to the 8th minus 1 equals 0. So y is 0 is one answer. And the other one, how are you going to get this one? You could do difference of squares. I like that. What else could we do?
Just move the one.
Just move the 1 over and then take what? The 8th root on both sides? You could do that. Take the 8th root of 1. But since you're taking an even root, you have to do plus or minus. If you do the square root, 4th root, 6th root, 8th root, right? You always have to do plus or minus. So you're actually going to get plus or minus 1. So we have 3 values of y that would satisfy these equations, right? Now I need to go figure out what x is. So what would x be? Well, it would depend on y, wouldn't it? So let me put this down here. Let's see. If let's take y to be 0. If y is 0, then go back to this equation right here. What's x? 0. So 0, 0 would be one of my critical points, right? Now let's look at another condition. What if y was 1? Then x would be 1 cubed is 1. So we get 1, 1. And finally, if y was negative 1, x would be negative 1. So we get negative 1, negative 1. So there's 3 potential critical numbers, right? Critical points. Once we have these, we can now go compute d, right? And when we compute d, as you're going to see in this problem, the d we get is going to be different for each of those points. In the last problem we did, it was negative 4, right? It made no difference where we were, we got negative 4. Here, you'll see d is going to change. You ready? No questions? I would like to point something out, okay, because I know someone's going to do this. 4y to the 9th minus 4y equals 0. 4y to the 9th equals 4y. Y to the 8th equals 1. Y equals plus or minus 1. What's wrong with that? What did I do?
Divided both sides by 4y.
From here to here, I divided both sides by 4y. And I accidentally eliminated one of my potential answers. Right? These two are correct, right? We got 1 and negative 1. The answer you're missing right now is 0. And the reason why you're missing it is because you divided by y, which made you promise me y couldn't be 0. You unintentionally got rid of one of your solutions, which is a big mistake. So anytime you ever see a polynomial equation, never divide through by a variable unless you are going to remember to go back later and check it. You know, don't divide through by something that could potentially be 0. It's always okay to divide both sides by 4. That's fine because, you know, 4 is never 0, but not by y. Okay, so please don't do that in this section or in especially 11.8. When we get to the next section, this is one of the big mistakes I see, and I don't show any compassion for that sort of mistake. All right, that's a college algebra thing. All right, so here we go. We're going to compute d. Let's just see if we can find a formula for d. d should be equal to this right here times this right here minus that, right?